Okay, in this video we're going to be talking through an aircraft problem. I like this problem because it combines a lot of different facets of mechanics into one comprehensive problem. So let's take a look. For number 1A, we are told that an aircraft is accelerating from rest along a horizontal straight runway, and we are asked to sketch the free body diagram for the plane. I'll start with what we know for sure, which is that there's a normal force upwards supporting the plane and a gravitational force downwards, of course. And those must be equaling out because the plane is not hopping up and down yet. We are told that it's horizontal straight on the runway. I'm going to say that the plane is accelerating to the right, so I'm going to draw a long arrow to the right. I might call this like force plane or force thrust or something to indicate that this is like the engines of the plane. And of course, there's going to be some sort of resistive force. That force could be air resistance, it could be friction. I'll call it the drag force to kind of encompass all of those in one. Notice that I've drawn the force of the thrust larger than the force of the drag, showing that we have unbalanced forces to account for that acceleration of the aircraft. Part B says the aircraft then reaches a large enough speed to take off. We are told the mass of the aircraft. The average net force on the aircraft while traveling along the runway is 70 kilonewtons. So this is the F net. The speed of the aircraft when it just lifts off is 70 meters per second. So we know at rest is when it started and it finishes at 75 meters per second. We're asked to estimate the distance, S, that it travels along the runway. There are actually two ways to solve this problem, and I'll show you both of them. The first of those ways, I'm going to start with Newton's second law, which is F net equals ma. Because we're told F net of 70 kilonewtons, and because we're told m of 8 times 10 to the third, we would be able to solve for acceleration a. This comes out to be 8.75 meters per second squared. We can then use that a in our kinematic equation. We know that the final velocity is 75. The initial velocity was 0. We just solved for a, and we're looking for s. This turns out to be s as 320 meters as our answer. The alternative solution, let's make some room. The alternative solution here would be to think about this in terms of work and energy, where you have the work being done by the airplane resulting in kinetic energy, or the work, which we could substitute as the force times distance, is equal to 1/2 mv squared. We know the average force. We're solving for distance. We know the mass. And we know the resulting velocity. If you would have liked, you could also have put initial kinetic energy, but realize that initial velocity is 0, so that goes away. And solving using this method also gives us the same answer. Part C. Part C says, while cruising at a velocity of 100 meters per second, the plane runs into a stationary bird. The bird dies and becomes stuck to the windshield. This is kind of gross. Explain how the force of the bird on the plane on the bird compares to the magnitude and direction of the force of the bird on the plane. The wording of this problem should make you think of something. Plane on bird, bird on plane. This should make you think of Newton's third law. Newton's third law says that for every action, there's an equal and opposite reaction force. Newton's third law will always follow that cadence. Plane on bird, bird on plane. So because of Newton's third law, we know that the force of plane on bird and the force of bird on plane are equal in magnitude but opposite in direction. If you're thinking to yourself, well, the plane was barely affected by hitting this bird, it barely even felt it, and the bird, as a result, really felt it, it died, you might be thinking about the accelerations. Even though their forces are the same, the plane has such a big mass that it accelerates just a little bit, and the bird has such a tiny mass that it accelerates a whole lot, and it dies. In CII, we are asked if the bird has a mass of 2 kilograms, calculate the resulting velocity of the plane and the bird. Now it's important to remember here that we are talking about an inelastic collision. Inelastic because the bird and the plane stick together. They share a common final velocity. Now for inelastic collisions, the only thing that we know is conserved is going to be momentum. Kinetic energy is actually lost to the surroundings in inelastic collisions. So we must use conservation of energy, conservation of momentum. The initial momentum is going to equal the final momentum. The initial momentum here is m plane times v plane. But the bird was stationary, so the bird itself has no initial momentum. The final momentum, though, is going to be m of the plane plus m of the bird, because they're stuck together, with a common final velocity that's together. If you prefer to write this as m plane times v plus m bird times v, that's also totally fine. I could do the distributive property on what I have written and get to yours. We know the mass of the plane and the initial velocity of the plane given as 100 meters per second. Again, the mass of the plane plus the mass of the bird, and we're looking for their final velocity together. Solving this out, it comes out to be that their velocity together, their final velocity, is 99.98 meters per second. Definitely enough to kill a bird. The next part of this question says, when approaching its destination, the pilot puts the aircraft into a holding pattern. This means the aircraft flies at a constant speed of 90 meters per second in a horizontal radius. The radius is going to be 500 meters as shown to the right. Part D says for the aircraft in this holding pattern, we want to calculate the magnitude of the net force on the aircraft. Show all your work. I know that net force equals ma, that's Newton's second law, but here the acceleration is something special. It's centripetal acceleration because we are in circular motion. I'm going to make a substitution knowing that centripetal acceleration is v squared over r. And I can start to plug in. I know that mass is 8 times 10 to the third. I know that v, given as 90 here. And I know r, the radius of the circle, is 500. This comes out to be 129,600 newtons of net force. And of course, we know that net force is pointed inwards or towards the center of the circle. After all, in order to maintain circular motion, you need that net inward force. Last but not least, part E says, unfortunately, the plane circled for too long and ran out of fuel. Luckily, the pilot spotted water ahead. If the plane is still traveling at 90 meters per second, when it is 800 meters above the ground, what speed will the plane hit the water when it lands? Okay, this is making me think of conservation of energy. We have some velocities, we have some heights, so we're thinking kinetic energy, potential energy, and this isn't actually the collision itself. This is talking about when it's high in the sky to right before it's hitting the water. So we don't have to worry about energy not being conserved like in an inelastic collision, because this is before that collision actually happens. So in order to conserve energy, you have initial energy equals final energy. Initially, we have kinetic energy and potential energy. And finally, all of that energy is going to go all to kinetic energy. This means 1/2 U mu squared, mgh, and 1/2 mv squared. I'm noticing there's an m in every term, so I'm going to cancel that out, save myself some time. And plugging in, we know the initial velocity when it's high in the sky is 90. We know the height when it's high in the sky is 800. And we're trying to solve for final velocity. This comes out to be 154.26 meters per second. Again, I really like this problem because there are many parts of mechanics that all came together here. We had a little bit of kinematics, we had some free body diagrams, we have Newton's third law, we had collisions and conservation of momentum, circular motion, and ending with the conservation of energy problem.